So today we will start chapter 3, material and energy balance. So this chapter will not be included in the exam. This should be an easy chapter because you already have it with material and energy balance course. So this will be considered a quick review of what you had so far. So this chapter we need to learn two things. We need to understand and apply the first law of thermodynamics to different systems. Here we are talking about open closed system. Anyone remember the difference between open and closed system? What's the difference? Anyone can say? Both of them, mass can cross the boundary. Closed system, energy cannot cross the boundary. Open system, mass and energy can cross the boundary. Yeah, so this is right. So it depends on the mass and energy, which one of them or both of them can cross the boundary. If none of them can cross the boundary between system and surrounding, then we have isolated system. But again, we will focus on open and closed system. And then we need to know how to use this first law of thermodynamics to analyze different equipment. Okay? In terms of the efficiency, we need to study the pump, we need to study turbines, compressors, nozzles, heat exchangers. So we will make all this analysis. So by doing this, we need to cover like 3 points actually. We need to start with the conservation of mass, then start with the first law of thermodynamics, which is conservation of energy. Then we will have several examples on applying the energy balance for different equipment. So just if you can imagine, if this is the chapter you have, just it's mainly 2 parts: conservation of mass for open closed systems, first law of thermodynamics, which is conservation of energy, and we need to use both of them to analyze different chemical engineering processes. Okay. So the first concept, the conservation of mass. So the conservation of mass, this one is the cornerstone of engineering. Anything that you need to analyze, the first equation you should start with the conservation of mass equation. Okay, so this is the basis of any engineering analysis you have. Basically, this principle said that the mass cannot be created or destroyed in a closed system. Okay, which means if you have any process, physical process, chemical process, the difference between physical and chemical process, these are processes that include or involve chemical reactions. Physical processes, any other process that doesn't involve chemical reactions. So if you have any physical or any chemical process except in nuclear processes, okay, nuclear processes is an exception. Conservation of mass not applied to nuclear processes, okay, but this is like beyond the course. We will not study these systems. So in physical and chemical processes, if you have a closed system, the total mass in this system will remain the same, even if you have reactions, even if you have phase change. So as long as the system is closed, okay, the system is closed, regardless you have chemical reaction, you have phase change, or you have just regular physical process, the total mass for this system will be the same. Okay. As we said, this principle, this is the basic or the first equation that we use in order to make analysis of any process or design of any process. So we can use it for just regular material balance problems. For reactor design, when you have the chemical engineering students, when you have this course, okay, in the reactor design, to design the reactor, you must study with the conservation of mass. If you will study the separation technology, separation processes, distillation, absorption, liquid extraction, all of type of separation process that we have in chemical plants, conservation of mass, this is the first equation that you need to use. Okay, even for environmental modeling, conservation of mass should be there. Okay, so this is the first equation you should think. If you need to analyze, you need to model, even you want to develop a mathematical equation to describe the behavior or the performance of the process, conservation of mass, this is the first equation that you have. Okay, and as we said, nuclear reactors are exceptions, but this is something we will not consider. The good thing for the conservation of mass that if you have a problem and you make the calculations just to check the conservation of mass, if the calculations does not close, which means the total mass, if you see any changes in the total mass, this is an indicator of a mistake in the calculations. Okay, so this is one of the steps that you can doubly check your answers. Okay, again, so the total mass of closed system should remain constant. No changes can happen in this one. So far is clear? Okay, now let's move to the equation side. This is the general balance equation we have. Okay, so the accumulation, anything accumulated inside the system, okay, which is rate of a change of the total mass of the system, because here we are talking about mass. This one is the result of whatever comes as inlet minus whatever goes out of the system, so inlet plus outlet, plus any mass generated inside the system or any mass consumed inside the system. So we have 5 terms. Again, the amount of mass or the total mass we have in the system is the result of what comes as an input minus what exit as an output, plus what can be generated inside the system minus what can be consumed inside the system. Okay? Let's see each of these terms. So mass generation, mass consumption, these 2 terms are related to chemical reactions. Okay? Mass can be generated if you have chemical reactions. Mass can be consumed if you have chemical reactions. If you apply to this equation to a product of a chemical reactions, so we have generation of mass. If you apply this equation to a reactant, okay, so the reactant is consumed. So again, mass generation, mass consumption, this applies for chemical reactions. If you have physical system, again, physical system means there is no chemical reaction, right? So if you are studying or analyzing physical system, these 2 terms will be 0. Okay? So this is the first simplification we can have in this equation. Just first, see, do I make analyzing for chemical system or for physical system? If it's physical system, no chemical reaction, so there is no generation of mass, there is no consumption of mass. Only if you have chemical reaction, then these 2 terms, one of them should be there, based on the substance you are studying. If it's a product, then you have generation of mass, then the consumption term will be neglected. If you are applying this equation to a reactant, so the reactant is consumed, so the generation term will be neglected. Okay? This point is clear? Okay. So let's say if we have open, non-reactive means physical system with single inlet, single outlet, so this will be the equation. Accumulation term, which is rate of a change of system total mass, rate of a change of mass. Rate, it means we have something divided by time. What is this thing? It's mass, because we are having conservation of mass. So the change of mass with respect to time. Rate of mass change inside the system equal inlet, mass flow rate of the inlet, minus mass flow rate of the outlet. This conservation is called the conservation of mass, but yet you can express the same equation in terms of moles instead of mass. So we know that number of moles is mass divided by molecular weight, right? So just you can substitute it in the equation, and then you will have dN by dt, the change of number of moles inside the system with respect to time, is the result of the inlet molar rate minus outlet molar rate. Again, generation and consumption neglected. Why? Because here we have non-reactive system. So I'm neglecting these 2 terms. So far is clear? Any questions? Okay. Now let's see this case. If we have open, non-reactive, so again, physical system, non-reactive means no generation, no consumption. But this time, instead of single inlet and outlet, we have multiple inlets, we have multiple outlet streams. If we have this equation that you apply to a single system, but now we have multiple inlet and outlet, what will be the change we have here?
You just have multiple inlets.
Yes, the only thing that we have multiple things. So it will be dm by dt, the same thing. This will be the summation, because here we have multiple. So we have multiple inlets, multiple outlets. So it will be the summation of inlet mass flow rate for all the inlet streams minus summation of outlet mass flow rate for the for all the outlet streams. And again, we can express equation in terms of mass basis or as molar basis. So we have dn by dt is summation n dot minus summation n dot in minus summation n dot out. If you need to check the consistency of the equation we have, so again, this is mass flow rate. Mass flow rate means mass divided by time. This is mass divided by time. This is mass flow rate. So all the sides or the terms of the equation have the same units. This is molar flow rate. molar flow rate. Molar flow rates means we have number of moles divided by time. So we have consistency in the units we have in this equation. Clear? Okay. Again, if you have all the equations we said right now, this is for open systems. But if we have closed system, okay, so closed non-reactive system with no inlet, with no outlet, so the inlet and outlet terms will be cancelled. So we have dm by dt will be 0, or dn by dt will be 0, or we have the initial mass equal the initial final mass, or initial moles equal the final moles. So all of these things just a simplification of the general equation we have above. Okay, so we start with the general equation, have 5 terms: accumulation equal in minus out plus generation minus consumption. So generation and consumption can be neglected if we have physical non-reactive system. Inlet and outlet, it can be single stream, multiple streams, or even we can have systems with no outlet, systems with no inlet, or systems with no inlet or outlet. And we have the accumulation term, and this accumulation term we will describe just right now when this term can be neglected. Okay. So these are the examples we have. If you have system with open system, this will be the equation that we used. If we have system with multiple inlets, multiple outlets, so just we have the summation term for the inlet and outlets. Okay, and again, this equation, either you can express it in mass balance or in mole balance. The same can be applied. Clear? Okay. Sometimes in these equations, we need to calculate mass flow rate, we need to calculate molar flow rate, we need to convert between these two things. So just to remember, in chapter 1, we discussed some of the properties of the substance. In chapter 1, we talked about the density, we talked about mass, some fundamental relations between these fundamental properties. So if you remember, we talked about density, and we said density is mass divided by volume. But if you have open systems, we are working with rates. So density is mass flow rate, which is mass over time, divided by volumetric flow rate, which is volume per time. Sometimes you need to calculate mass, so you need to calculate density, and density is not given, but you have something called specific gravity. Specific gravity, this is one of the properties you can use to calculate the density of any substance. So specific gravity of any substance equal the density of this substance divided by density of a reference substance. And what if this reference substance is water? And the density of water is 1000 kilogram per meter cube, or 1, this is 1, not 1000, 1 gram per centimeter cube, or 62.43 pound mass per feet cube. Okay. Sometimes you need to calculate the volume. The volume is not there, but I can give you dimensions of the system. I can give you the cross-sectional area. I can give you the length of the system. So I can give you the dimensions, and just this area times the length, you can calculate the volume. Volumetric flow rate, it's volume divided by time. And as we said, volume is area times length. So we have area times length over time, area times length, area divided by time, this is velocity. So volumetric flow rate, you can use it as area times velocity. Sometimes you need to calculate mass flow rate in the equations. So mass flow rate is density times volumetric flow rate. And volumetric flow rate is area times velocity. Okay? Or sometimes we have the specific volume, which is volume divided by mass, or reciprocal of the density. So mass flow rate is area times velocity divided by the specific volume. So all of the equations that you can use here, these are like basic conversion of these fundamental properties. So based on the given information you have, you can substitute in any one of them to find what is the mass flow rate that you need to calculate, the molar flow rate, the volumetric flow rate, if you have the density. So these are the basic like units you need to solve the equations. Okay, just to start finding the values of the molar flow rate of the inlet, molar flow rate of the outlet, and these things. So far it's clear? Any questions? Finished writing? Okay. We have this table here. This table just is the summary of everything we explained so far. Okay, so the general equation, special case of the equation in case of a steady state, what will be the equation in case of open system, in case of closed system, the general equation in terms of the mass balance, difference form with the special case for open system, for closed systems. So just this table gives you a summary of all the equations we presented in the previous slides. Okay? But again, there is no need to memorize all of these things. Just if you know the equation, you understand each term, then you can make this derivation very quickly. It will not take more than just 1 minute, and you can do it. But just in case, if you need to doubly check, at the time you are make this derivation and you need to doubly check the final equation, if this is the correct one, you can compare it with the table that we have here. Clear? Okay. Let's take this example. So this example, it says compression of steam. Let me put this one to get the numbers. So this one says we have a vessel. This vessel initially contains 5 meter cube of superheated steam at 300 degrees Celsius at 1 bar. The vessel is sealed out, but it's equipped with a piston cylinder arrangement so that the volume can be changed. If the steam is compressed to 5 bar, what will be the new total volume? So we have steam inside this system, the initial volume 5 meter cube, we have this temperature 300, we have this pressure, then the pressure change at 5 bar at the same temperature. Temperatures remain constant. So you need to know what will be the new volume we have in this example. So in order to solve this one, this is a closed system. There is no mass exchange between the system and surrounding. So again, the rule is the total mass inside this closed system will be constant, or can it change? It will be constant, right? So this is the key here. So I know that there is no change will happen in the mass. So the mass in the initial state will be the same mass at the final state. So I can use this rule in order to find the volume I have. So in order to solve this one here, so we'll start at the initial condition. So initial condition, I have superheated steam this superheated steam at 1 bar 300 degrees Celsius. Okay. So now, if you go to the appendix, or the Excel file for the steam table, just put the information here. 1 bar 300 degrees Celsius for superheated steam. You will find the specific volume of this one. It will be 2.639 meter cube per kilogram. And what is the specific volume? Specific volume is volume divided by mass or mole. Specific means you have the property divided by mass. So specific volume is volume divided by mass. So this means if you need to find mass, so it will be the volume divided by specific volume. At the initial conditions, the volume is known, and the specific volume, we just obtain this one from the appendix, so we can calculate the mass here. So this mass will be 1.98 kilogram. So at the initial condition, initially the mass we have is 1.89 kilogram. So at the final condition, we will have the same mass, right? Because closed system, no inlet, no outlet. So based on conservation of mass, total mass will be constant. So based on conservation of mass, principle, the total mass will be constant. So if we go to the final condition, so now for the final condition, we know that the temperature T2 is still 300 Celsius. and P2 pressure at the final condition is 5 bar. Use these two conditions, go to the appendix, so you can say then from the appendix the specific volume at the final condition this one will be 0.5 to 6 meter cube per kilogram. But again, this is not required. We need to find the final volume, not the final specific volume. But we know that specific volume is volume divided by mass. Then the volume, which what we need to calculate, is specific volume times mass. So volume at second condition equal all of this one. So the volume, this one will be here 0.5226 times the mass, which is 1.89. So you can substitute in this one, and the final volume will be 0.99 meter cube. And this is what we need to find. Clear? Any questions? Okay. Let's take this last example here. This example says we have 4-liter sink, initially half full of water. So we have full 4-liter sink, half full of water, so the initial volume of water we have is 2 liters. The faucet is turned on and 1 kilogram per minute of water begins pouring into the sink. So this one is considered inlet or outlet?
Inlet.
Again, this one is considered the inlet, yeah. The faucet is turned on and we have this one start pouring into the sink. So this is an inlet. At the same moment that the faucet is turned on, the drain is opened and 10 centimeter cube per second, and this is the outlet, of water flows out of the sink. How long after the faucet is turned on will the sink overflow? Okay, so here we need to find the time. So we have inlet, we have outlet, the rates are different, so we need to find when this sink will overflow. Okay, how we can solve this one? So this system considered open or closed system? Open system. So here we have open system. Let's start with the general equation. We have accumulation equal in minus out plus generation minus consumption. Do we have any chemical reaction?
No.
Nope. So the generation and consumption will be cancelled, right? So if you write this equation, so you have accumulation is dm by dt. We have just one inlet, so we have m dot in. One outlet, so we have m dot out. Okay. Let's see what we have. We have this one, inlet mass flow rate. This is given. The inlet mass flow rate is 1 kilogram per minute. For the outlets, we know that the volumetric flow rate of the outlets, but we need the mass flow rate of the outlet. So what is the relation between them? Is density. So density is mass flow rate over volumetric flow rate. So this means if you need to find mass flow rate, it will be the density times the volumetric flow rate. Okay, the volumetric flow rate is in centimeter cube. Density of water is 1 gram per centimeter cube. So this one can be 1 times 10. So this one will be 10 gram per second. So now just to check the consistency of the units, we have this one kilogram per minute, and we have this one is gram per second. So we don't have consistency. One of them should be converted to the other one. Okay, let's say we will convert the first one here. If we will convert this kilogram per minute to gram per second, so m dot of the inlet, it will be 1 times 10 to the power 3 to convert kilogram to gram divided by 60 to convert this one to second or minute to second. So this will be 16.67 gram per second. So just substitute in the equation right now. So you have dm by dt. This one will be 16.67 minus 10. So it will be 6.67. Separate the variables. So we have dm equal 6.67 dt. Then we need to have by integration. So integration of dm from initial mass to final mass equal 6.67 integration of dt from t1 to t2. So we have m2 minus m1. This will be 6.67 delta t. This is what I need to calculate. Okay, but I have no idea what is the mass. I know that initial volume is 2 liters, right? But I don't know the mass. So I can convert mass to volume. So I have M1, this will be rho times V1. And in terms of the units we have, density is 1 gram per centimeter cube, volume is 2 times 10 to the power 3. And this one, to convert liter to centimeter cube. So if you did this calculation, so you have the initial mass will be 2000 gram. The same thing I will do for M2. So M2, this is rho times V2. Rho is 1. V2, this is the volume of the water in sink when the sink is full, which is 4 liters. Again, 10 to the power 3 to convert liter to centimeter cube. We need to have consistency in the units. So this one will be 4,000 grams. So substitute in the example here in order to calculate delta T, and then delta T you have, this will be 300 seconds, which is almost 5 minutes. So from the moment that you open the faucet and the drain, this tank or this water will take 5 minutes until it will start to overflow. So again, here we try to apply the conservation of mass principle to find this information.